So you'll notice they can word it with the word rotations, or they could say a cyclist is riding around a circular track, right? That's the same thing as telling you how many rotations something went, right? Keyword here, they said diameter, a diameter of 62.5. And how far has he traveled after completing 175? Now we have the word laps. That is just a rotation because it is a circular track. And so this is where we did our rotations. Well, we went around it 1.75 times. So we have 1.75 circles. And then we need to think about what is the circumference of a circle, because that will be how far he's traveled, right? Circumference of a circle is 2 pi r. And so we have 2 pi times r. Now, keyword here was diameter. So what do we need to do to that r? To get that r, what do we do with the diameter? Cut it in half. So we're going to say 31.25 here. And then we're going to use 3 significant digits when we do this. This guy traveled 343 meters. A radar antenna rotates clockwise through 195 degrees in 0.85 seconds. What is the angular velocity of the radar antenna in radians per second and RPMs? So for both of these, we are going to do some type of conversion. I like to teach it the way you're thinking of how many degrees do I have compared to an entire circle, right? And that kind of tells you how many rotations you've had. So if I'm thinking of rotations, but they've given me an angle, I'm going to say, well, first of all, the word clockwise is important because in this world, clockwise is negative, right? And so the first thing I'm going to think is, well, I have negative 195 degrees. And an entire circle is 360 degrees. So I'm always going to say, how much of a circle do I have, right? I have 196 out of 360. Now for radians, I have to convert that circle, however many circles I have, to radians with that 2 pi. All right. And then remember, I'm going to take how far I traveled divided by how much time it took. Now you can, in your calculator, you can say divided by 0.85 seconds. For the next one, we're going to convert to minutes. So we're actually going to do 1 over 0.85, but it's still the same. All right. And then we have it. We have our radians per second. In this case, we're looking at 2 significant digits. We have -4 approximately, probably depending on how we rounded in that process, but something like that. Question has 2 pieces to it. It also wants RPMs. R there is not radians, right? It is rotations. So we do not have to take this and convert it. All right. All we have to do is take this same thing, the 195 over 0.8 over 360. And now we're just saying we have it in seconds. Instead of division here, I'm actually going to say 1 over 0.85. That's just so that my conversion factors make sense, right? So 1 point over, that's just division. But they want RPMs. So I will automatically have it in rotations here. I have it in seconds. The only thing I need to convert is that M, that minute. And so I'm going to say, well, how many seconds are in a minute? That's going to cross cancel up here with that 1 minute down here. So when we're doing our conversions, just as a reminder, seconds is what I'm dividing by, so seconds needs to go in the numerator to convert it. And then I'm literally just multiplying across. So I'm going to do, in my calculator, I can do all of this. I can say -195.8 divided by 360 divided by 0.85 times 60, and it will do order of operations for you, right? And you should get, again, in 2 significant digits, approximately -38 RPMs. Again, that's just, most of the time RPMs will be in positive. You'll hardly ever see RPMs in negative. all you're doing is you're saying clockwise, right? You're saying clockwise there. A grinding wheel in a machine shop rotates at 4,200 RPMs. The machine is turned off and the wheel slows to 700 RPMs in 5.5 seconds. What is the average angular acceleration of the grinding wheel in radians per second squared? All right. Before I do anything, I need to get these RPMs into radians per second. All right. I need to get them into radians per second. Because then if not, I'm going to be comparing rotations to seconds. There's going to have to be another conversion. So typically it's easier to go ahead and convert those rotations to radians per second and then divide by second so that you don't have this weird minute second conversion, which is fine if you do, but again, you can go ahead and convert it if you want to. So, all right, so either way there has to be a conversion. You have to write out. So let's say we're just going to go ahead and subtract. This is rotations, and I'm going to leave it at the end. We have 4,200 is where I started. Actually, I'm going to do the other way. You do ending first, so you know if it's slowing down. 700 is where I ended. 4,200 is where I started. That is going to be in rotations per minute. And then I'm dividing by seconds, right? So I have to do this conversion here. What you have to realize is that when you have a denominator over a denominator, this is like minutes, seconds here. The denominator drops to the bottom with that other one. So when I do this conversion, I don't want you to think, when you do it this way, I don't want you to think that he's up there. He's a denominator piece. So we'll see that when we do our conversion. Again, this is rotations, not radians. So I am going to do that same multiplication here. That's my radian conversion. To go from rotations to radians, we multiply by 2 pi. And then it wants it in radians per second squared. And right now, I'm going to be in radians per minute per second, not per second squared. So my minutes here are on top. So my minutes, bottom. So my minutes will go on top. My seconds will go on bottom. This is where you don't want to make that confusion with that RPM. And again, you can convert the RPMs first if you want to, and then just do radians over seconds, and then you're done. Either way, that conversion has to happen. This is going to be 2 significant digits. So we're at approximately negative 67 radians per second squared. All right, radians per second squared. This is also a 2-part question. This is my first. To figure out how far something that's on the point of that wheel would have traveled, we're just going to take our radians per second. And I will tell you that when I do this multiplication over here to go to this next step, I use the long, non-rounded piece typically. So I do significant digits for my final answers. I try to keep it as close as possible as I go. So this is about, I think, what I got when I put it in. And you just take that number and literally multiply it by the radius. Make sure it is radius that they've given you. Make sure that's a radius that they've given you. And I think you end up, it traveled. And again, this is a magnitude. So if they had said how far, like a distance, you would have done absolute value. But because they use the word magnitude, we're talking about a vector. So negative 19 meters per second squared for that acceleration as well. So if yours says 5.50, that actually is for the first answer. Then you would go to 66.6. That's a fun biblical number there. All right, so you would actually go to 3 for this one, but you would not for the second one. The second one, unless it's different on yours, that time comes into play, and that's only 2 significant digits. So since you're doing division there, you're going to go with that lower one. This is calculating angular displacement. So we have to calculate how far it went, and then we're going to have to plug it into one of our displacement formulas, right? So kind of like our change in theta. This is going to be a radians answer. They gave us rotations per minute. So once again, because that's rotations, and you can even write rotations and you can write minute if those R's throw you off, you do have to convert it to radians. We cannot do rotations for a distance, so we do have to convert it to radians. And my acceleration is in seconds, not minutes. So I do have to convert that from that minutes, 1 minute, to that seconds. All right. It is decelerating, so that is a negative there. Decelerating is going to be a negative. You can use it here or you can use it in your division when you use your acceleration. You just need to make a note that that answer is going to be negative. All right. At the end, because it is a displacement, we can keep it at positive. But as you go through this, think about what they're asking you. And so this is going to be about 10.5. Remember, this is from the formula. And it's your ending minus your beginning. They're both squared, and then you're dividing by your 2 times your acceleration. In this case, angular acceleration. So on the front, if you use that one, it's like the change in x. And on the back, if you use that one, it's like the change in theta. That's all the way over to the right. And so we're using the formula that we have a change in theta, and we're going to use our omegas. We're going to use our final omega squared minus our initial omega squared over 2 times that average angular acceleration. That's the formula we're using. There we go, 115. So we're going to use our final, which is stopping. So when we think about what these mean, final is a stop, all right? Initial, that's going to be the 1100 RPM, but converted, all right? So this is my stop, is my final omega. Converted to radians is my initial omega, all right? And so now we're ready to plug it in. Our final was 0. Our initial was the 115, and we're going to square it. Obviously, technically, if we were not at 0, we would square that too, but it doesn't matter because it's 0. And we are going to divide that by the 2 times the average acceleration, which is that 22.5. And now we're ready to actually find out our displacement. Okay? When you put this in your calculator, parentheses have to go around that denominator. So you're going to put a negative in front. You're going to say 115. You're going to square it. Divide. You do have to open parentheses here before you do this multiplication, or it will do order of operations, and it will divide by 2 and then multiply that whole answer by your 22.5, and you will have a much different answer. All right, so in how many significant digits? So you should get approximately something like this, right? Keep going. Yep. Yep. And so then you want to drop it there. So negative 290, and we are in radians. I corrected all of them because they had them all backwards. Your heavier weight needs to be at the end of the seesaw. If it's not, your other guy's going to have to be off the seesaw. So just so you know, he's got to be further away. So 4.5 meter seesaw. Remember, that is the entire length of the seesaw. We have our 2 weights here, and it's just like the bell work. It's going to end up, if I want to know, and I would personally probably label like an X and a Y here so that I know, okay, if I'm going to put this one out at the end, then he is going to be the 2.25 away, and I'm going to do that, and then I will divide by the smaller one in order to find my distance to my smaller one. You can use AB, you can use XY, but I would label those 2 so you remember which one you're talking about. And then, like I said, this ends up being just like our bell work. He should be in 2 significant digits. So in 2 significant digits, you should get approximately 2. More difficult. I don't go all the way out. So this one, you're going to just leave the whole distance because you're adding the 2. So that should be both of them. Again, if you label them, this should be both of them added up. So the first guy and the second guy, right? But you're going to have to rewrite one of them just like you did above. So you're going to have to rewrite one piece of it and not the other. And it doesn't matter which one you do, because you're just finding one and subtracting from the whole distance for the other. So remember, you're saying whichever one I choose to use, it doesn't matter. But one of them I'm going to use, and I'm going to pull it out and end up having that division, because I don't know what he is. That's what we're always going to have. Always, always. You're going to end up the two forces divided plus one, and then we're solving for one of those. So if I'm solving for either one, I'm going to set it up with its distance. Let's say I am calculating his distance. It's going to be how far away is he divided by, and that's where we get that from that one we just did above, plus that distance again, because we've done a substitution here. So it's always going to end up looking like that. It's going to be the total distance, whichever one I'm solving for, that goes with the numerator divided by the other one plus 1. And so in your calculator, again, you can do the whole thing, 3.5, you can divide by that whole crazy group. And in your calculator, it will do order of operations, just like that. And you will get one of them, in this case 1.8, and that tells you the numerator distance there. That tells you the numerator distance. So if they ask for a specific one, like in this case, they're asking for the 530, you want that guy to be on top, right? So that way you know the difference.